Before any new idea, let me hand you one picture to hang everything on. Think of a house wired to a single master switch. Flip that switch on, and every room lights up at once. Flip it off, and the whole house goes dark together. For a square matrix, that master switch is one word: invertible. Turn it on, and a whole family of good properties come on together. Turn it off, and they all fail at once. Today we learn to read that switch. Here is that switch opened up. For an n-bind matrix A, there isn't just one test for invertibility. There are 7 different looking statements, and they are all secretly the same statement. Let me reveal them one at a time. 1. A has an inverse, a matrix that undoes it. 2. Its determinant is not 0. 3. Its rank is full. All n rows and columns pull their weight. 4. Its columns are linearly independent. None is a combination of the others. 5. The only vector A sends to 0 is 0 itself. 6. For every right-hand side B, the system AX equals B has exactly one solution. And 7. 0 is not an eigenvalue of a Now watch what ties them together. Every single one of these is equivalent to every other. Double arrows, both directions. Knowing any one hands you all the rest. So the whole web rises and falls as one. When the matrix is invertible, every node lights green. All 7 are true at the same time. And the instant it is singular, every node flips red. Not some of them, all of them together. There is no in between. Let's make that real with 2 little matrices. On the left, 2, 1, 1, 2. On the right, 1, 2, 2, 4. Check the determinant. On the left, 4 minus 1 is 3, non-zero. On the right, 4 minus 4 is 0. That single number decides everything else. So the rank split, full rank 2 on the left, only rank 1 on the right, because its second row is just twice the first. The null spaces split too. On the left, only 0 goes to 0. On the right, the vector 2 minus 1 is crushed to 0. A whole line of non-zero solutions, and so 0 is not an eigenvalue on the left, but it certainly is on the right. One column green, one column red, and every row inside a column agrees with the switch. The web is about invertibility, but some facts hold for absolutely every matrix. Invertible or not, square or not. These are your anchors. Let's meet them, each with a tiny check. First anchor. The rank can never exceed the smaller of the row count and the column count. A 2 by 3 matrix has at most rank 2. It simply has no room for a third independent direction. Second, multiplying matrices can only lose rank, never gain it. The product's rank is at most the smaller of the two. Two rank-1 matrices can even multiply down to rank 0, a fact we'll turn into a trap later. Third, and the one you lean on most, rank plus nullity equals the number of columns. Every dimension is accounted for. What the matrix keeps, plus what it crushes to 0, always adds up to n. So for 3 columns, if the rank is 2, the nullity is forced to be 1. You never have to guess the null space dimension. It's whatever's left over. Fourth, transposing a matrix leaves its rank untouched. Row rank always equals column rank. The number of independent rows is the number of independent columns for every matrix there is. Fifth, a beautiful pair for square matrices. The trace, the sum down the diagonal, always equals the sum of the eigenvalues, and the determinant always equals their product. Quick check with eigenvalues 2, 3, and 4. They sum to 9 and they multiply to 24. Hold that thought. We'll see exactly that matrix in a moment. And the last anchor is a gift symmetric matrices give you. If A equals its own transpose, then all of its eigenvalues are guaranteed real. No complex numbers can sneak in. Take 2, 1, 1, 2. Its eigenvalues are 1 and 3, both real, exactly as promised. And better still, every symmetric matrix is diagonalizable. That fact sits quietly under principal component analysis. Let's tie every one of these threads to a single matrix. Here is W, upper triangular, so all the action sits on and above the diagonal. We'll compute every invariant and watch them agree. Because it's triangular, the eigenvalues are just the diagonal, 2, 3, and 4. So the determinant is the product, 2 times 3 times 4, which is 24, non-zero. So W is invertible, and the whole green web lights up. Its trace, 2 plus 3 plus 4 is 9, which is exactly the sum of those same eigenvalues. Determinant is their product, trace is their sum. Both checks pass. Now rank and nullity. The determinant was non-zero, so all three columns are independent. The rank is a full 3, which means the only vector W sends to 0 is 0 itself. The nullity is 0, an empty null space. And rank nullity closes the loop perfectly. 3 plus 0 equals 3, the number of columns. One matrix, determinant, rank, nullity, trace, eigenvalues, and every single invariant agrees. That's the synthesis. Here's a second worked example, built around the fact that catches people out most often. To tempting claims that being invertible forces a matrix to be diagonalizable and that a repeated eigenvalue forces it not to be. Both feel true. Both are false. And one counterexample each is all it takes. Take J, upper triangular. Its determinant is 2, so it is firmly invertible. The green web is on. Its eigenvalues, read off the diagonal, are 1, 1, and 2. But solving for eigenvectors, the repeated value 1 hands back only a single direction, not 2. So J has just 2 independent eigenvectors, and it needs 3 to be diagonalizable. Invertible, yet not diagonalizable. The first claim is dead. Now the second claim. Both of these matrices have the repeated eigenvalue 1. The identity is already diagonal. So, of course, it's diagonalizable. But the shear 1101 has the very same repeated eigenvalue 1. And it is not diagonalizable because it too has only one eigenvector direction. Same repeated eigenvalue, opposite answers. So the lesson is sharp. A repeated eigenvalue decides nothing on its own. What settles diagonalizability is the number of independent eigenvectors. Count those, never the multiplicities. Your turn. Here is a matrix B. Pause the video and answer to questions. Is it invertible? And what is its rank? Look hard at those rows before you continue. Here's the tell. The second row is exactly twice the first row. The moment two rows are proportional, they're dependent. So the determinant collapses to 0. 0 determinant means B is singular. The whole web goes red. And the two surviving independent rows give rank 2. So by rank nullity, the nullity is 1. If you spotted the dependent row, you read the switch perfectly. Now 4 traps that catch almost everyone. Trap 1. The rank of a product is not the rank of A. It can drop. Take a rank 1 matrix times another rank 1 matrix, and the product can be rank 0. Multiplication is allowed to destroy rank. Trap 2. The determinant does not split over a sum. It is emphatically not linear. Take A and B both the identity. A plus B is 2 times the identity, whose determinant is 4, not 1 plus 1. The determinant of a sum has no simple formula. Trap 3. You cannot add eigenvalues either. The eigenvalues of a plus B are not the eigenvalues of A added to those of B, unless the two matrices happen to share the same eigenvectors. In general, adding matrices scrambles their eigenvalues completely. And trap 4. A subtle one. A non-zero determinant means invertible in theory, but it does not mean safe in practice. This matrix has determinant 1/10,000th, technically non-zero, so the switch is on. But it is a whisker away from singular. Its columns are almost parallel. Its condition number is enormous, and inverting it amplifies every rounding error. Invertible and well-behaved are not the same thing. Let's lock it all in. First, the web. Invertible, non-zero determinant, full rank, independent columns, trivial null space, unique solutions, and no zero eigenvalue are all one and the same. One switch, 7 faces. Second, the accounting anchor that holds for every matrix. Rank plus nullity equals the number of columns. Nothing ever goes missing. Third, the eigenvalues quietly carry the determinant and the trace. They multiply to one and add to the other. And fourth, symmetry buys you realness. A symmetric matrix always has real eigenvalues and is always diagonalizable. Hold the web and these anchors together, and no always true question can surprise you again.